Welcome back to another video, everyone. I thought my next video was going to be continuing talking about integration, but it was requested by a lot of people to talk about the inverse trig functions and not secant, cosecant, and cotangent, but rather the arc versions of sine, cosine, this stuff. The -1 notation showing that it is the inverse operation, such that if sine of theta equals x, then arcsine of x equals theta. Okay, so the inverse function to the normal trig functions. What would the derivative of such a function look like? Well, to start, let's consider arcsine of x and try and find the derivative of that. So, we already know this. Based off of this Pythagorean identity, we know that cosine x can be written in terms of sine x like this, square root of 1 minus sine squared x. Now, here's something interesting. How about, instead of cosine x, we change the input from x to be arcsine x? Well, what will that equal? This square root won't change, this 1 minus won't change, but the x over here is the same x here. So the arcsine x here must be the same arcsine x that is going here. But what's sine of arcsine? Well, because you're taking the function of the inverse function, by definition, you just get x, and then it's still squared. So we see that this is true. Cosine of arcsine x is equal to the square root of 1 minus x squared. We can use this information to derive the derivative of arcsine x by taking the derivative on both sides. It will remain equal because these functions are exactly equal. So this is what that process is going to look like. Cosine of arcsine x is equal to square root of 1 minus x squared. Taking the derivative of both sides, on the left side, we'll have to employ the chain rule. The derivative of cosine is negative sine, and then times the derivative of the inside is the derivative of arcsine x. We don't know what that is yet. And then that is going to be equal to, here, it's the power rule. This is also the 1/2 power, so the 1/2 comes here. And then 1 minus x squared to the -1/2 is going to be 1 over, so it's on the denominator, and then it's still square rooted. And then multiplied by the derivative of the inside because of the chain rule. And that chain rule will give us -2x, but of course that multiplying by 2, and then the 1/2 will cancel, so our final expression is -x over root 1 minus x squared. Now, sine of arcsine x is just x, and now finally dividing both sides by -x, we get that the derivative of arcsine x is equal to 1 over the square root of 1 minus x squared. Now, you can use the same exact method to find the derivative of arc cosine x, and we find that it's exactly the negative of the same expression. -1 over square root of 1 minus x squared. So that's arcsine and arc cosine out of the way. Now let's get to tangent. We can use a similar method by taking this identity. Tangent squared plus 1 is equal to secant squared. Rearranging and then putting in arcsecant x as the input, we find this expression. Now let's take the derivative. Taking the derivative on both sides, for the left we find the derivative of tangent is secant squared, so secant squared of arcsecant x times the derivative of the inside, which is arcsecant x, is equal to, and you'll get this expression by employing the same process of chain rule and power rule. Now, secant of arcsecant x is just x, and it's squared, so we have x squared times this is equal to x over root x squared minus 1. Divide both sides by x squared, and you get this expression. Now, here's something to consider. The graph of arcsecant x looks something like this. Now, the problem with this is that this has a derivative which is always positive. See, if you take here, positive derivative, positive derivative, positive, still positive, even though it's really small. Now, what that means is that for negative values of x, our current expression can have a negative output because the square root of x squared minus 1 will always be positive because it's the square root, and so we have to consider this. This x cannot be a normal x, and we have to add an absolute value. Following the same processes that we've been using thus far, we get an expression for secant of arctangent x as square root of x squared plus 1, taking the derivative of both sides. On the left, the derivative of secant is secant times tangent, so we get this expression, and then on the right, we'll get x over root x squared plus 1. Now, this all simplifies. Tangent of tangent, arctangent x is very simple, that's just x, but this secant of arctangent x, well, that's weird, right? Except we already have an expression for it right here. It's just the square root of x squared plus 1. So we plug that in here, and then the derivative comes down as well. Dividing both sides by x, this x will cancel and this x will cancel. And when you divide by root x squared plus 1, you'll be multiplying it in the denominator, and the square root will cancel, and you will get this expression. So the derivative of arctangent x is equal to 1 over x squared plus 1. And so the final list of derivatives will look like this. The derivative of arcsine, 1 over root minus x squared. Arccosine, the negative of that. Arcsecant, 1 over absolute value of x times the square root of x squared plus 1. Arccosecant, the negative of that. Arctangent, 1 over x squared plus 1. Arccotangent, the negative of that. So as we see, if you go through the same methods that we use to derive arcsine, arcsecant, and arctangent, you will come to the conclusion that whenever you add this co in front of it, you're going to get the negative of the original function. Now, that's an interesting pattern, and I won't talk about why that is here, but this is the list you'll need to know. So, thank you so much for watching.